Hello, for Data Communications and Network 1 class today, I'm Usana Tantulaves from Ksesat University. For this clip, I will talk about two topics. The first one is analog data to digital signal, or AtoD. Sometimes we have heard of this as AtoD converter, right? Another topic is the analog modulation. Okay, so let's look at the first topic. AtoD is a method that we convert analog data to digital signal, okay? And in this figure that I show here, you have a digitizer. Digitizer will change the analog data. This is voice, okay, analog data to digital signal here, okay? And then, so this is basically AtoD, okay? And then when we want to use it in practice, okay, we may have to combine it with the digital modulation, okay, sometimes if you want to send it in some frequency band, okay, that we want, okay. So we have a digital modulator here, okay, that change the digital data. This one is, for example, 01101, okay, into analog signal, okay, to be transmitted like ASK here. So basically this is 01101, okay, because 0 you send nothing, okay. So I show you this, okay. This is combination of AtoD and the digital modulation. I show you this because I want you to notice that the input is analog and output is analog, but they are not the same, okay. They're not the same waveform, okay. The input is analog signal that carries analog data, but the output is analog signal that carries digital data, okay, so that you will not be confused, okay, on how to use this, okay. So first part is AtoD, the second part is digital modulation. Now we will go into how to do the AtoD converter, okay. We do this, okay, by using the pulse code modulation. And this is the block diagram of the pulse code modulation. Let's look at the steps, okay? The first step is PAM, or pulse amplitude modulation. You sampling, okay, the analog signal. So this is the analog signal coming in, input, analog signal. You sampling it, okay, by sampling with the same time difference, okay? So the same like delta, the same sampling, sampling period, okay. So this one you sampling it, okay. Now it's become discrete in time because it's only have, this is the PAM signal, okay, it's only have values at the given time like T0, T1, T2, but the amplitude is still analog. Amplitude can be anything, okay. The amplitude can be anything, it can be any real number. So discrete in time but continuous in amplitude. This is your PAM, pulse amplitude modulation signals, okay. This is after the sampling, you get this, then you quantize it, okay. Now, okay, let's look at the sampling a little bit more. If you have heard of the sampling frequency using the Nyquist, okay, Nyquist sampling rate, okay, so usually you sampling more than or equal to 2 F max, okay. F max is the Nyquist sampling rate. You probably have heard of this before in principle of communication, okay, I believe. F max is the maximum frequency of baseband signal, okay, of your baseband signal that you want to convert, okay, your analog data. Okay, so this is the sampling frequency. Now after you sample it, you will quantize it, okay. Quantize is that you make it to be discrete in both time and amplitude, okay. PAM is discrete in time, but PCM will be discrete also in amplitude, okay. Now let's look at this. It's this one, okay, but let me draw again, okay, like over here. So I have this, and then this one, and then this one, right? So I will divide the level here like this, okay. Now I will quantize it by make into the closest values, okay. So let's say this is closer, let's say closer to this one, to the level that is closest to, okay? So suppose it's this. So this is the original value. This is the quantized values, okay? Quantized. So let's say this is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 0, okay? Something like this, okay? So after I quantize, I will get over here, okay, PCM, okay, signal. Then I will encode it into digital data by reading the values, okay? So the first one is 0, 0, 1, 0 here. The second one is 0, 0, 1, 1, and the third one, okay? The quantized value is 0, 1, 0, 0, like this, okay? If I have another one, it's probably going to be here. Suppose it's here. And I have this quantized value. It's going to be 0, 0, 0, 1, okay? Okay, so this is the digital data over here, okay, that you transmit. So this is how you do the user PCM, okay? So after you quantize, you get PCM. After you sampling, you get PAM, okay? Then you encode into digital stream that you can transmit, okay, using line coding or using digital modulation. Okay, this is the A to D converter. Now the next topic is analog modulation. This is the more common term, okay? But in our class, okay, we have also another term, which is analog data to analog signal, okay? So that we can distinguish between the analog data to analog data to digital signal, something like that, okay? Analog modulation that we have heard about is AM, FM, PM, okay? Especially these two, okay? Amplitude modulation, frequency modulation, phase modulation, and the application, radio transmission, okay? You have AM radio, FM radio, okay? Those are the applications, okay? Now let's look at AM, okay? In the AM or amplitude modulation, we will change, okay, the amplitude of the carrier, okay, to follow or to correspond, okay, to the amplitude of the baseband signal, okay? The baseband signal will become the envelope of the carrier. Let me show you the figure of what this means, okay? This is my baseband signal, okay, the low frequency signals, okay, in time domain. And this is my carrier. My carrier is sinusoid signal, sine omega ct or cosine omega ct, okay? This one I use sine over here because start with 0 phase here. This is sine. Then this is my AM signal after I modulate. You can see that the amplitude of the carrier varies, okay, based on the amplitude of the modulating signal, okay? So this envelope look like this, okay? Now let me show you how to sketch it, okay? If you do have to sketch the AM signal, suppose you have the signal baseband look like this, okay? Baseband look like this. What you do, okay, is that you will move everything up to be above zeros, okay? This is baseband. You move everything up to be above 0, so I move it here. And I will draw it as the dotted line here. Then I put a mirror here in the middle, and I draw the mirror reflected image, okay, over here. Okay, then I will draw my carrier signals inside. This is my carrier signal. Okay, you can see that my carrier varies based on the amplitude of the baseband. Now this is become my AM signal. Okay, be careful that the envelope has to be dotted line. Okay, dotted line because you don't actually send the envelope. You send the high frequency signal, the carrier signals. Okay, just that the amplitude follow, okay, the envelope Okay, so you, okay, if you draw it like this, this will be wrong, okay, because if it's a solid line, it will be wrong because it seems like you send both of the signals together, okay, but actually you send inside, send what is inside the envelope only. You send the carrier only, okay, and this make it possible to send through the antennas, okay, of the high frequencies, okay. You do the amplitude modulation because I have talked to you about this before, because the wide frequency is very low, okay, you have to have a very big antennas, but if you move it into modulate into the higher frequency, then you can use smaller antennas. Now let's look at how to do this in terms of the device, okay. So you have input baseband coming in, you multiply with this is the carrier, okay, which is sinusoid, okay, and this is oscillator, okay, oscillator that gives you the sinusoid. You multiply together, you get this is the AM signal. Okay, now let's look at the bandwidth of AM. We have again discussed this before. It's the same as the ASK, PSK, and QAM bandwidth, okay? The common word that we use like AM signal that we talk about, this is double sideband transmitted carrier. This is the common name that we refer to this case. The transmitted bandwidth, okay, of the AM signal would be 2 times of the baseband frequency of the baseband bandwidth. Okay, if you remember, I have drawn this in the last clip. Okay, so you multiply by the carrier here, and then you get something like this. Now this is FC, so this is 2B, right, or 2B sub M, if the B sub M is the baseband frequency. Okay, so this is what we have here, 2 times of the B sub M. Okay, this is the double sideband transmitted carrier, or AM signal in general. We actually have, okay, in the technical term of amplitude modulation, we have many cases, okay, and one case is called single sideband, or SSB. Single sideband, we send only one sideband, okay. Usually we send the lower sideband. This is the sideband. On the left and on the right, okay, they are the mirror of each other, so they have the same information. So you can send only one sideband, lower sideband, okay, and this part is upper sideband, upper sideband, okay. Okay, so the lower sideband usually use less bandwidth, so use a lower frequency, okay, so we prefer lower sideband usually, and we do not send the carrier, okay. So we use only half of the bandwidth here. So single sideband use only B sub M hertz, okay, as the bandwidth. So it's good, right? But usually it's very difficult to do, okay, to do in a good quality. There's one band application that we can use single sideband, okay, which is voice. Okay, so this is a very good, okay, advantage to send to transmit voice, okay. So you can use single sideband, you can save half of the bandwidth. But if you send other signal that is not voice, usually it's difficult to do for the single sideband, and I don't want to get into this as I usually explain in detail in the principle of communication class. Okay, so you can take a look at it by yourself, look it up, okay, why single sideband is not good for other signals. Now let's look at the frequency modulation. In this case, the frequency of the carrier will vary, okay, with the amplitude of the baseband. Frequency of the carrier, okay. The amplitude of the carrier remain constant as the input and the output, okay. So the amplitude of FM signal is also constant, okay. This is very different from AM because AM amplitude of the AM signal varies with the carrier, right? the amplitude of the AM signal vary with the baseband amplitude, but this one remain constant. Require more bandwidth than AM. We will talk about this in the next slide. So we have, this is baseband signal in time domain, okay? And then this is dual carrier in time domain. You don't actually multiply, okay? This is actually VCO. VCO is voltage control oscillator, okay? This one, okay, the output of VCO is that the frequency of the output signal depends on the amplitude of the input. So this device gives you this, okay, VCO, okay, this one VCO, okay. Frequency of the output signal vary with the amplitude of the input signal, okay. So you can see that this is your FM signal. Amplitude is constant, as I told you before. This is time domain, amplitude is constant. Frequency change, okay. Low frequency, high frequency, we can approximate the amplitude like this. So this is low frequency, so it has to be low amplitude, right? And then high, so high amplitude, then low amplitude, and then high amplitude like this. So we can guess this is the baseband signal, okay, which is correct, this one, okay, correct, okay, because for high amplitude of the baseband, the frequency is high frequency. Low amplitude of the baseband, okay, is low frequency, okay, changing like this, okay. So this is the FM signal. Now let's look at PM signal. For PM signal, the phase of the carrier varies, okay, with the amplitude of the baseband, okay. Sometimes we call it modulating signal, okay. And FM and PM, we call it modulated signal. FM, PM, AM, we call it modulated signal, okay. The amplitude of the carrier is constant, and amplitude of PM is also constant, okay, of the modulated signal is also constant. Require more bandwidth than AM. We will look at this in the next slide, okay. Let's look at the picture here, okay. So you have, this is baseband. This is your carrier, which is psi omega CT, okay. Then this is your PM signal, okay. You can see that you cannot approximate, okay, approximate the amplitude, okay, this with this as FM, because it's changing the phase. Very difficult to look by, with your eyes, okay, to detect with your eyes how to sketch, okay. Now let's look at how to make it, okay, in the device, okay, how to find, to get PM. So this is your baseband, okay. Get into, you have to dip first, because you dip the phase, you got frequency, right? After you dip the phase, you got frequency. Then the input frequency go into the VCO, voltage control oscillator. You get output signal that varies from the frequency of the input, okay. And this frequency of the input is actually the result from the differentiate, okay, of the amplitude of the baseband, okay. So this is how you make PM signal, and this is the formula, okay, for the PM bandwidth, okay. We'll look at this in a little bit, okay. Bandwidth of FM and PM. The modulated signal, okay, that I have mentioned, okay, can be of FM and PM can be expressed like this, okay. So they are the same. The difference is the phi t are different, okay. It's different. For PM, the phi t is just the constant phase modulation index multiplied by the baseband signal. MT is the baseband signal, okay. But for FM, the dip of the angle, this is like the angle, right? The dip of the angle is the multiplication of the frequency modulation index, which is a constant, with the baseband. Okay, this is different. So you dip the phase to get the frequency, right? Okay, so this is the derivative of the phase. Now let's look at the bandwidth. Carlson's rule, this is important. It's the same formulas, okay, for FM and PM, but the difference is that beta is different. Beta for PM is the phase modulation index, okay, multiplied by the maximum amplitude. But for PM is the same, okay, with the frequency modulation index, but it has to divide it by 2 pi b. This is the difference. PM is the bandwidth of the baseband, and AM is the max value of MT. But the max value doesn't concern about the sign, okay? So let me show you this. If you have MT, look like this, okay? And this is -5. This is 2, okay? AM equal to 5, okay? We don't we look at the most variation from the 0 values, okay? We don't actually look at the size. So this one in the formulas have to be 5 here. So this is the end of analog modulation, okay? And this is the reference. Thank you very much.